So hello everyone. Today we shall see that how to change the sampling rate using the discrete time processing, that is changing the sampling rate by discrete time processing. So far what we have studied, that we have x of n is equal to xc of nt, where x is the continuous time signal xct, which can be represented by a dt signal x of n. Okay, so if xn is given to us, so we had seen that how to reconstruct the continuous time signal, for which we have used the band limited interpolation formula, and that formula is given this by xr of t is equal to summation over n from minus infinity to infinity of x of n times the ideal reconstruction filter. Yeah, which gives your x of n is equal to xr of nt, and it is equal to your xc of nt. So this shows that the samples of xc of t and xr of t are identical at the sampling times, even when your xc of t may not be equal to xr of t for all time t, but at the sampling time they would definitely be equal. Yeah, this is what we had seen so far, but now we shall see that in fact it is often necessary to change the sampling rate of a DT signal. So in this we had seen that we did the sampling of the continuous time signal at time t, but now we need to construct a new sequence which is sampled at some time t1, and it is not equal to the capital T what we had just seen. So that is what we want, that x1 of n, that's why I defined this new sequence x1, and it is equal to your xc of n t1, where your t1 is not equal to t. Okay, and we call this process the resampling process. So one of the ad hoc approaches, or trivially the first method comes to your mind, is that you can obtain x1 of n from x of n by reconstructing xc of t from x of n, right? Using that above formula, using this formula. So first of all, what you can do is you can reconstruct the signal xr of t from x of n, which is sampled at some time t. Now since this relationship is satisfied, so you can reconstruct, in fact you can resample xc of t with period t1 to obtain x1 of n, right? This is a trivial method. So from the discrete time signal, first of all we construct the continuous time signal, and then I resample that continuous time signal at at the desired sampling time, let's say t1, which is not equal to t, to again sample, discretize the signal to obtain finally x1 of n. But generally this approach is not practical, because we had seen already that only at the sampling time those signals are the same, even when you don't have this equivalence for all time t. And in fact it is not also a practical approach because of non-ideal reconstruction, filter, D to A converter and A to D converter, what we had seen the cascaded blocks in some previous classes. So here the objective is to change the sampling rate using only the discrete time operations, right? Only dt, only by performing the dt operations, change the sampling rate. This is what we want. So first of all, we shall see that uh, the sampling rate reduction by an integer factor. And later we shall see the sampling rate, increasing the sampling rate by some integer factor. Okay, and we only want to do this resampling by using the discrete time operations only. So let's define a new sequence. Define a new sequence as xd of n, which is the resampling. So whatever the x we have, that integer factor is some capital M, and from the above relationship this becomes equal to xc of n mt. This capital M factor is included in the previous equivalence. But if we see the block diagram representation of this equation, so what we want to do, we have this x of n, the sampling period is capital T here, and we want to reduce the sampling time by some n. This is the representation we shall going to use to yield a new sequence xd of n, which in fact is equal to x of n. Here the sampling period is td and equal to mt. So we call it the sampling rate compressor. So there are many names to this process. Sometimes we call it the sampling rate compressor, sometimes we call it the downsampling, but the overall term we use the resampling. Okay, so xd of n, this xd of n is identical to the sequence that would be obtained from xc of t by sampling with period td is equal to mt, and this is what we want to achieve. But we cannot do the continuous time operation since we had seen that it is not a practical approach. Okay, but we want to ensure the inherent property of this resampling. Okay, so let you have the continuous time signal having the property that xc of j omega is equal to 0 for mod omega greater than omega n. Okay, then your xd of n is an exact representation of xct. If you have pi by td, which in fact is equivalent to pi by mt if I replace the td by mt, and it should be greater than or equal to omega n. So what does this imply? It says the sampling rate can be reduced to pi by n without aliasing if the original sampling rate is at least m times the Nyquist rate. This is the Nyquist rate. So if I take this vector here, this is what it says. So the original sampling rate, because t is the original sampling rate and is at least m times the Nyquist rate, then you won't have any aliasing. We shall see also from some of the examples or some pictorial description that when does the aliasing occur and when does it not occur. Okay, so the operation of reducing the sample rate, like I said earlier, that we call it the downsampling also. Right? So let's see in the frequency domain all this analysis, that how we can obtain and what are the implications and the significance of some of the steps which we carried out. Okay, so in the frequency domain, when you have x of n is equal to xc of nt, we have a nice frequency domain representation of this. We had seen many times earlier that x of e to the power j omega is equal to 1 upon t summation of k from minus infinity to infinity of your the Fourier transform representation of your continuous time signal xc j omega by t minus 2 pi k by t. Okay, so these are the two time domain and frequency domain pair. Let's say when we had the samples, when we had the sampling process at some capital D. Now for this new sequence xd of n, we have this x of nm and it is equal to xc of n td with td is equal to mt. Okay, so for this the frequency representation we have xt of e to the power j omega is equal to 1 upon td. Now we are carrying out the sampling process at some time td and it is the summation over r. Let's use some another index r from minus infinity to infinity of this signal xc j omega by td minus 2 pi r by td. It would remain similar to the above with t replaced by capital TD. Okay, so we can replace this TD by this m of t, let's say. I'm just carrying out this additional step so that you can make your own notes as well. Empty, empty, and empty. Okay, because we have this TD is equal to empty. So writing this now, this is an important step. I can express this index r as equal to I plus k times n, where k and I, both of them are some integers, such that you have k varying from minus infinity to infinity, and we write I varying from from 0 to m minus 1. Okay, so we shall see from some figures as well that how you have obtained this I only from 0 to m minus 1. Okay, note that having k and I like this, you still have r lying between minus infinity to infinity, because it should not change from here, because the initially we have this index varying, or we are carrying this summation over r minus infinity to infinity. For any I lying between 0 to m minus 1, since we have k varying from minus infinity to infinity, we would still have r from minus infinity to infinity. So whatever the property we had initially for this equation, it would still hold with this I and k pair. Okay, let's substitute this r here, and explicitly writing this above equation, we have xd of e to the power j omega as let's write this 1 upon mt summation. Okay, let me repeat this equation once again. Okay, we have this empty, we have I plus km and w upon mt, and here we have empty, and here we have I plus km, because our r is replaced by this. Okay, so having this R, I can decompose this summation as the summation of as two summations with two different indices as I and k. So explicitly writing that decomposition, I can write as 1 upon m, the first summation from I is equal to 0 to m minus 1 of 1 over t. I can take this t inside, this another summation, and another summation we have k from minus infinity to infinity xc of j, and I can combine this omega and 2 pi I. So omega minus 2 pi I, or let's write this separately to have the better visualization. We have j times omega by mt minus 2 pi k by t and minus 2 pi I by mt. Okay, this is what we would have, right? Or we can see the implication of this, that why we have this I0 uh, to m minus 1. Okay, but before that, let me write what does this internal summation signifies. Okay. So also, if you see from this equation, particularly this, if I shift the omega, if I shift this omega by omega minus 2 pi I by m, which would replace by here, so you would notice, okay, first of all, let's replace that omega. So we had x e to the power j, and what we want to do is to replace the previous omega by omega minus 2 pi I by m. Okay, and writing that expression, it would become 1 upon t summation over k from minus infinity to infinity of x of c, and you have j omega minus 2 pi I by m minus 2 pi k by t. Okay. So see the similarity between this expression and this expression, whatever you have inside in the curly bracket of the previous equation. So I can express my xd of e to the power j omega as 1 by m summation over I is equal to 0 to m minus 1 of x, because I'm now replacing this whole thing by this x, by x of e to the power j omega minus 2 pi I by m. Okay, so now we have represented our xd in terms of x, and xd what we had initially from xc. So let's see, first of all, what is the, why we have replaced this I varying from 0 to m minus 1. So see this figure, where read this xc, which is a continuous time signal xc, and your capital F is the big omega, the notation what we have been using. So this is the omega s. Okay, so wherever you see x and in subscript a, so those are the continuous time signals. So here we have some continuous time signal in this a, and in the frequency domain we have this xc of omega, right, with this f. And here now if I do the sampling of this signal at some sampling time t, which is given by 1 upon fs, so this is the discrete time signal what we obtained, and in the frequency domain it would be periodic, okay, at every sample time, okay, of this xc. So this we had seen earlier, and now I want to resample it at some time which is 2t. So here our m is equal to 2. So now I want to obtain another signal x of n where we have resampled this x at 2t. So seeing this continuous time signal, the original continuous time signal, if you want to sample it from the given continuous time signal, this is what you will obtain in the figure C on the left hand side. This is the exact sampling, because here we are doing the direct sampling from the continuous time signal, because if the continuous time signal is given to us, we can resample it at any time until it is satisfying, or if we want to do the reconstruction, if it is satisfying the negative sampling theorem, we can also reconstruct it without any aliasing phenomena. Okay, so here you would see this xt when I sample it at some time 2t. Okay, so in this figure D, if we have m is equal to 4, this is the signal what we would obtain in the discrete time, direct if we do the sampling from the continuous time signal. And in the frequency domain, this is what happens. Okay, here we see some aliasing phenomena, but okay, we will come to this aspect a bit later. But why we have this I varying from 0 to m minus 1? Because if you see from the original x, if I draw a straight line, I mean you can see from here, if I draw the straight line from here, from of the original x of f, then you see only both sides you have only m minus 1 times repetitions, because here we have m is equal to 2, so we get only 1 extra. That's why we do it I varying from 0 to m minus 1. Now for the case of m is equal to 4, we should have three kind of this frequency response. So here we have this 1, 2, 3 and 4, which is not coming entirely because we had this aliasing phenomena. So that's why we have I is equal to 0 to m minus 1, and here for m is equal to 4, we would have I varying from 0 to 3. Okay. So coming back to where we left, at this place where we have this two different representation of xd in terms of x, a discrete time sequence, and in terms of xc, which is a continuous time sequence. So from this xd, what you notice that it is composed of the superposition of an infinite set of amplitude scaled copies of xc and amplitude scaled by 1 upon m, and frequency scaled omega as omega is equal to big omega td, and shifted by integer multiples of 2 pi. Okay, I will repeat once again. So it is composed of the superposition of an infinite set of amplitude scaled copies of xc of j omega, frequency scaled omega is equal to big omega td, and shifted by integer multiples of 2 pi. Now if we pay attention to what we have obtained here in terms of the discrete time sequence, the frequency representation of the discrete time sequence, so it is composed of the superposition of m amplitude scale copies, of the periodic Fourier transform of x of e to the power j omega, frequency scaled by m and shifted by an integer multiple of 2 pi, because I is an integer here. So you can have two implications from two different representation of xd. One, which is a direct representation or direct relationship between the original sampled signal at some time t and in terms of the continuous time signal itself, because this is pretty much straightforward. It is like doing the sampling at what we did at some time t here. So here if we just replace t by td, you would obtain this xd of e to the power j omega directly from the continuous time signal. Likewise we had seen in the previous figure. Okay. Now, okay, we can uh, try to see what it implies in from some figures. Okay. Okay, let's see. You have this xc of j omega, the frequency domain representation of the original continuous time signal, and this is your xs, which become equal to with this relationship, and on the time axis we have this the big omega, huh? And you have this omega n. And from here you can obtain x of e to the power j omega by scaling the frequency as omega is equal to big omega t. So all these omegas would change to rewrite this omega n as omega n t pi into pi. This is pi. Okay. Now, using the representation what we had obtained, or the relationship between xt, the frequency domain representation of the resampled signal xt, and the frequency domain representation of the sequence initially sampled at some time t. This is what we had just written by opening up that summation, because it would be for I is equal to varying from 0 to m minus 1, and here we have m is equal to 2, sorry. So here we would have only for I is equal to 0 and I is equal to 1. So this is the frequency domain representation of xt e to the power j omega when you have omega scaled as big omega td. But now putting it in terms of omega, so to compare, so this is what we have obtained. Again, we can see from what we had seen earlier that if I draw a straight line from here, right, so this is what you obtained. Okay, so here you don't see any aliasing, but as we saw earlier that with m is equal to 4 there was some aliasing phenomena was occurring, right? So we can now see what would happen if we downsample by a factor of m is equal to 3, right? So we obtain the sequence as xdn is equal to x3n, which would be equal to xc of n3t, replacing m by 3, okay, whose frequency response is plotted here in figure C. Okay, this one. So taking that same xc what we had seen in the previous figure, and this is x of e to the power j omega. Now for m is equal to 3, you notice that there is some aliasing phenomena is occurring. With normalized frequency omega is equal to big omega td. Note that because m omega n, which is 3 omega n, is equal to 3 pi by 2. What I want to say that m omega n is equal to 3 pi by 2, where omega n, sorry, this is capital N, omega n would be omega n td. Okay, it is equal to 3 pi by 2, which is greater than pi. So we, from the previous theory, we know that the aliasing would occur. So in general, to avoid aliasing in downsampling by a factor of m, we require that your omega n m should always be less than equal to pi, or your omega n should be less than equal to pi by m. In fact, this is what we had seen when we were talking about this implication. Okay. So if this condition does not hold, the aliasing would occur, right? Now, if we want to avoid the aliasing, we can do the downsampling if in our design procedure we are willing to reduce the bandwidth of the signal x of n of this signal. So if we reduce the bandwidth of the signal before downsampling, we can still avoid the aliasing. So let's see. So what we would do? First of all, we filter the signal x of n by some ideal low pass filter whose cutoff frequency is pi by m and gain is 1. Then whatever be the output, let's denote it by some x tilde of n whose frequency response is drawn here, which is capital X tilde of e to the power j omega. So this we would obtain the frequency domain in the frequency domain, right? What we want to do, that this x tilde of e to the power j omega is equal to hd e to the power j omega times x of e to the power j omega, what we had initially. So this is the resulting frequency domain representation. So note that the sequence x tilde of d, this x tilde of d is equal to your x tilde of nm, no longer represents the original underlying continuous time signal xc, because this is what you have, this x tilde d, and all this part is moved. So if I want to reconstruct my original continuous time signal, you cannot do it. But what you can reconstruct, that from x tilde d of n would become equal to some x tilde c at ntd, where td is again equal to m times t, and x tilde c, this signal, is obtained from xc by low pass filtering with the cutoff frequency uh, at, by this low pass filtering with cutoff frequency omega c at pi by td or pi by mt. So here we have the the cutoff frequency would be the same. You can apply the same filter, low pass filter, to the original signal xc to obtain x tilde c. So when we reconstruct from this resampled signal x tilde of d, you would obtain x tilde of c, but not the original signal. So this is what we can do. So in overall, the implementation of the downsampling we do in this way, that from the previous block diagram. So in the previous block, this is the generic representation of the compressor. But since to avoid aliasing, what we will do, given this signal x of n, we pass it, first of all, we pre-process it before resampling. And by pre-processing, we pass it to some low pass filter whose gain is equal to 1 and cutoff frequency is equal to pi by n to obtain some signal x tilde of n, right? So here x of n, we had this signal was sampled at some time t. This is also sampled at some sampling period t, and now we downsample it by some integer factor m to obtain your x tilde of d n as equal to x tilde of n, where the sampling period is now td, which is equal to m times t. So this is the generic block diagram representation for reducing the sampling rate by some integer factor capital M. So here you would see that whatever the processing we have done, all is done in by using the discrete time operations only. And because we know that once we have the continuous time signal, we can always we can do the sampling of this original continuous time signal at any time t. Okay, so we can stop here today. So in the next class we will see the rest of the part when we want to increase the sampling rate by some integer factor. Okay, thank you.